So, hi everyone, it's my pleasure to announce Ali Mohammad's talk, How to Search a Gallery Image Using Text.
Yeah, hi everybody. I'm Ali. I'm a PhD student at ITMO. Today I will discuss the problem of searching a gallery of images using a text. Feel free to add me on LinkedIn using the QR code appearing here, and let's get into it. So let's start by setting the motivation and the reason why we need such systems or why we need such intelligent systems. So actually, uh, if we want to talk about cross-modality information retrieval, it's important because nowadays on the internet we usually see the internet the data on the internet represented in coupled form. So we would see an image with a caption, like on Instagram, for example, and we would see an article with some images. So it's very rare actually to see one modality without the other. So it's very important nowadays. It's usually presented in coupled form. It also have many applications in e-commerce, in social media, and for custom tasks. For example, if you are a photographer, for example, and you happen to take a lot of images, then probably you want to have some tool to search through your own personal gallery. Also for e-commerce, people like to uh, describe what they want to buy, and then people get frustrated if they don't see the product that they had in mind right away. So it's very important for e-commerce, for social media, for all kind of tasks that involves searching uh, through images or other stuff. The main problem in this kind of systems is that uh, image text matching is inherently ambiguous problem. If we look at these three images here, you can see, well, we can find a minimum query that describes all three of them. Perhaps, I don't know, white walls, white room, some white furniture, something like this. Well, we can find some kind of minimum common query. But if we take a deeper look, we can see that there is some differences between these images. So if you say in your query, I want a white room with some green plants, then you probably don't want to see the image to the right, but either one of these two images to the left. So as you can see, the query it's very ambiguous problem. It's not clear what kind of results the user expects. It depends on the situation, of course, and that's what make this kind of problem very challenging and interesting at the same time. So in the bigger picture, what we want to do is to create this system. We would have an image modality or a visual modality. It can be a database, a big file, if you want to, like a set of images, anything like that. And we would have some search query, some textual modality. We want a model that can inference similarities between our search query and our gallery of images, and then retrieve the information for us. First, let's talk about how to solve this kind of problem, both in classical and more recent literature. So the classical and the more straightforward approach is to use off-the-shelf models. How to do that? Okay, we have an image, we have a text, we have models that are great at understanding images, and we have models that can easily understand text. So, okay, let's create a representation for each modality separately, and then maybe we can try to find some kind of matching or similarity or distance between these representations. As you can see in the image, like we would pass the image through an image encoder, and then we had a separate encoder for the text, and then maybe a neural network to try to find matching between these two different spaces. The problem with the classical approaches is that it's very complex to train and to maintain such a system, and it has low performance. It does not build a native connection between the two modalities. So the natural solution is actually comes from transformers. Transformers are a more recent or fairly modern architecture. It was originally introduced for text, and it depends on multi-head attention. You can check the link in the QR code for more information about transformers, but the idea is that we have a sequence as an input, and the transformer job is to try to find attention or information dependency between the tokens of the input sequence. So if you have a sentence, then each word is a token, and then you want to find dependencies between different words and try to extract useful information from that. But the question here, can we generalize this and use transformers for the visual modality or for both textual and visual modalities? Well, the answer is yes, we can. So let's do it. Okay. If we want to use transformers for cross-modality tasks, what do we need? So as we understand, we have the text. We can easily transform a text into tokens and use it for transformer. For images, actually, there was a paper from Google called "An image is worth 16 by 16 words." And it's very important and very actually interesting paper. The idea is very simple. We can handle an image the same way we handle a sentence. We can split it into tokens and then use a linear projection to create some simple representation, the same that we do with word embedding for the textual modality. And what do we get? We get a long list of tokens as it appears here in the image. So the blue ones are the textual one. The pink one are the visual or the tokens that comes from the image. And the idea is simple. We split the image simply into slices. And each slice, again, through linear projection, can be used as a token for a huge transformer encoder. So the advantage here is that this transformer at the same time looks at slices of the image and words from the sentence. So at the same time, it understands both modalities, and that's the essence of what we want to do in this task. So this idea was used successfully for what we call a VILT, a vision and language transformer. Again, the link in QR code to this paper. So here, the authors, they used several downstream tasks to train this transformer encoder. So again, we have the sentence, the visual, and the textual tokens. We have three heads. We have text image matching, which is a simple label, 1 or 0. Basically, it represents if the sentence belongs or is a good caption for the image or not. We have masked language modeling, which is interesting. It is a generative task for the textual modality. Basically, if you apply a mask to the sentence and you want the model to predict the missing word. So in this example, a stone, statue, near, and mask, and the answer is office. So it's a generative task for the textual modality. And we also had word batch alignment, which is basically trying to align each word in the textual modality with each slice of the image. Very interesting. But the most interesting part is that we have a generative task for the textual modality, but we don't have one for the visual modality. So in my work in the master's thesis, we tried to fix this problem. So we added mask batch prediction, which is a modification that allows a generative task for the visual modality. We were trying to overcome the disadvantages of VILT of the original one. So the idea is very simple. What we want to do is for each slice of the image, we want to predict the mean, the average pixel value of this slice. And by that, it's a simple but very powerful method to trigger the model into understanding the visual modality more efficiently. So what we did is that we fine-tuned our model into image text matching, mask language modeling, the generative task for the textual modality, and then we added our MPP or mask patch prediction for the visual modality. The second modification or the second try that we did is about single batch prediction. So again, we are trying to add some generative task for the transformer, but we want to add this generative task for the visual modality, not for the textual one. So the textual one is MLM, mask language modeling. It's very famous, widely used. But here in this example, we used what we call single batch prediction. And the idea is that we hide one part of the image, and then we replace it with a learnable mask, which is a common technique for those who know about BERT. And we pass it through the linear projection and then use all the tokens for the transformer. And on the other side, on the heads, on the targets, we want our model to predict this patch, this missing patch, this missing mask. And the third case, we tried to generalize the previously mentioned approach, and we wanted to hide multiple parts of the image. But here there is a small modification. Here we use the mask after linear projection, not before. The reason is we don't want to if we use the mask before the linear projection, it will require much more resources to train. But if we use the mask after projection, it would need much less resources. So basically, we add the mask simply to inform the model that there is a missing part here, but it's not as important as the mask before. And here we try to trigger the model or to teach the model how to regenerate the full image. So if we hide some parts of it, similar to what we do in masked language modeling, we want the model to regenerate both the sentence and the image at the same time, and also to predict if they are the same or they belong to the same pair or not. So we try to do all this. When we look at the results, like quantitative results, we tested on the COCO dataset, and we noticed that our first approach with the average pixel or the MPP, the mean patch prediction, we achieved around 1% more on image retrieval or on COCO dataset, more than the original VIT fine-tune, and around 6% more than the zero-shot one, which is very good, actually, given that we only modified the small task. We also using our SPP, so the single batch where we predict only one batch. We trained only for 10 case tips. For reference, the original one was trained for 100 case tips, so around 10% of the training, but we achieved very competitive results. We had like 39% recall at one, and in comparison with the zero shot, it's like more than the zero shot, but still less than the fine-tuned one. And finally, using our RMPP, where we try to recreate the full image out of the input, we had much less success on recall. And I believe the reason was it was a very complex task. For 10 case steps to, again, here we use around 10% of training steps than in comparison with the original VILT. And I believe it's much more complex and requires more training and more data. Here is an example of what we did and visualization of what we are capable to do with such models. So to the right, you can see that we can simply select one word from the input, and then we can visualize which parts of the image are most essential to this word, or like most correlated with this word. So here you can see, and to the left, you can see simple search queries. So a giraffe in the zoo, and the results, of course, is a giraffe in what looks like a zoo. So you can see like a visualization of how the system works. To the right here, we can see a very detailed example of how it works. It's, of course, it's not easy to get into the mind of a transformer model, but it seems that the correlation makes some sense. So, for example, if we're talking about football, it kind of shows legs and balls and stuff like this. So the second part of my work was about qualitative results. So we had a basic idea or a simple idea on how this system's performance should be measured. So we designed an experiment. We had a Telegram bot, and we asked people to use it for search. And the setup was as following: we would show the person an image, and then we would ask them to provide a simple caption for this image. If the system shows the same image or something similar to it, so something that satisfies their query, but doesn't have to be the same image that we showed in the first step, then they can leave a like, or they can leave dislike or unlike or something like this. And here is the interesting results. So we had a recall percentage of about 50% likes and less than that for dislikes. But for rank one, which is when we have the top result from our database search, we had only around 30%. So here I'll repeat to make it the point more clear. If we show an image to a person and ask them to write a caption for this image, and then we search our gallery of images, and we can retrieve the same image that we showed in 30% of the cases. But in 50% of the cases, the user is anyway satisfied with the results, even though it was not the same. And it's actually more correlated with rank 5. So when you have your result in the top 5, which is very interesting. And also, it's worth mentioning that we had 2 native speakers, English native speakers, and they had much higher accuracy or higher recall when it comes to searching. It's obvious, of course, but it was very interesting. So let's jump into chapter 2, or how to improve text image search. So as we saw, if we use only recall metrics is not enough, because what we really want is user satisfaction, or how users look at the results and how they receive the results. And also it's interesting to notice that there is no text retrieval task. So we are talking about image retrieval, so why not text retrieval? Well, it's actually easier to generate text than to search for it. And maybe the same can be said about images. So maybe it's easier for some queries to generate an image that represents this query than to use retrieving systems. And the third point is, what if the query lacks some context, or what if it did not precisely describe the content of the image? So we can look at this example. Here we have an image. Maybe what we can say about this image, maybe we can say, yeah, it's a line of cars in the street waiting for the green light. But actually, we can say something totally different. We can say random street in autumn in New York City. And actually, that was the query that I used to get this image from Google Images. So as you can see, sometimes we want to write some query that does not necessarily describe what we will see in the image, but it does describe some semantic relationship between these objects, or maybe something that comes from the vibes of the image. So that would be our theory. So let's say that there is no precise mapping between the set of all possible queries and the set of all possible images. Another way, we cannot precisely describe all what appears in the image except using the image itself. So the most accurate representation of an image is the image itself, and we cannot write a precise representation in text. And this ambiguity should be taken into consideration when we train such systems. So we should understand that each query can represent multiple images, and each image can correspond to multiple queries at the same time. So what ideas can we use to improve this? So the first one is to try and not too much images and text as we described, and to use non-binary matching. But here the challenge is how to implement such a system, because there is no obvious similarity function that can be reliably measured between any image and any text. The second approach that we might take is similar to what we saw in this seminar, and where we use purely generative methods for pre-training. So actually, if we try to regenerate the caption and regenerate the image, we can train very good model, and this would have this ambiguity embedded into it. And the third approach that we can take is to use some kind of weak annotations. So if we understand that there is no bounding between text and images, then we can use maybe a huge data set, or not very huge, but a weakly annotated data set, where each image have some kind of caption, some kind of textual representation, but not necessarily very accurate, or not necessarily describing the objects inside the image. So for now, that would be all. I welcome any questions, and if you have any ideas or comments about this, please do provide it.
Yeah, so thank you very much. Please, dear listeners, if you have any questions, free to ask. So, okay, looks like it's time for me to ask questions.
Okay.
Generally speaking, you are talking about the direction which now is called foundation models, as you have quite a big model, not super big, but still it's transformer, which you train on downstream tasks. So this is basically what foundation models are designed for, to work with multimodality on different tasks, to be pre-trained on different tasks and yield better performance on each of them, or at least some of them. So talking about foundation models, like how do you locate your research in this domain?
No, I'm sorry, can you repeat that?
Yeah, okay, like in terms of foundation models,
Yeah.
in this domain, okay, maybe I'd better ask you the first question, because foundation models is like trend of a couple of years, so maybe like I'm familiar with them.
To some extent I'm familiar, yeah, but not deeply. So if I understand the question, so you want me to, or the question is about is about where do I see this kind of model, so text image search in this,
yeah, like
big space?
Yeah, because actually the research on how to work with different modalities and train on different tasks is what foundation models for.
Yeah.
So terms like as you never referred to them, I'm trying to ask like, it's not like how you see connections, because obviously there is a very straightforward connection, but what is the place of your research in this domain, and how do you let's say see so it's actually it's hard to ask, because like you're talking about a very precise thing, but you don't mention anything, so I'm just trying to have connections.
Okay, if I understand the question correctly, so here's the idea. So yeah, if we are talking about foundation model or founding model, then we are talking about something that can understand, well, anything like let's say we have visual, and like, let's say we have an image, a video, and a text, and the sound maybe, and then something that can understand any kind of models between them. Okay, if we want to take the subspace of models that can understand both images and and text, then we expect these models to, for example, generate an image out of text, or generate a text for an image, or maybe even image to image transformation, or something like this. Well, when we talk about search, it's a little bit different, but the way I see it, it's fundamental to have some kind of knowledge, like deep knowledge between, and deep ability to transform between different modalities in order to achieve very good search. Because, well, as we saw in the classical approaches, if you want to take a classical approach where you try to learn each modality separately and then try to create some matching between them, like the classical approaches used to do, then you have a fundamental problem that usually the textual modality is not representative enough of the image. So yeah, it will describe something in the image, but it will not describe all the image. So how I see it like as a task, I guess, inside this big framework, and a very important one. And maybe even it's much harder to search for an image than to generate one, because when you generate, you have like all the imagination and the abilities to generate whatever you want. But if you want to search into limited space, you have to really understand what is the most important thing in the search query. That's how I see it.
Yeah, okay, thank you. So this was quite general and like more theoretical question. So yeah, I guess it's hard to just what you didn't answer. So okay, my second question is about the downstream tasks. So on the first part of the research, so where you created some downstream tasks, but they were mostly on how to improve, let's say, image manipulation. So I believe that maybe there is a good idea to just try to create downstream tasks which would be helpful to work both with texts and images. So for instance, like to predict what is depicted on this patch, so which word is related to what is written on this patch, or okay, this is just a very basic idea, but I believe that more better designed ideas of how to combine both modalities for downstream tasks, so that would improve not only image processing, but also image processing with the idea of mapping it to the modality of texts.
Yes, that's actually, well, here there is 2 points. So the first point is, yeah, this is absolutely correct. So when we use this kind of generative tasks for the visual modality, it kind of shift the attention of the model into the visual modalities. But at the same time, let's remember that this is a transformer, and it's inherently embedded in this model that it tried to find connection between the different tokens. So actually, if we just inform the model that this is a visual token and this is a textual token, and let it build its own attention, and that should be enough to make it understand like both modalities at the same time. So like, what's the advantage of adding one more head just for alignment between these two? It's like it sounds like just a part of what exists, but of course, like let's remember that the original writers had this word batch alignment. I just removed it for simplicity, but it will be very interesting actually to try to come up with something more advanced, maybe, or maybe controlled generation of the images using the text. So like you use part of the input text to generate part of the image, something like this. That would be actually very interesting, yes.
Okay, so thank you. And okay, then could I ask you to just show the very last slide with the ideas for future work.
Uh,
Yeah, this one. Yeah, so okay, actually the first question is very big, and it's based, let's say so, on predicting functions. So there is a very good and well lightened path of how to work with dependence when we match from X to Y. But once we just make a step from this path, everything becomes much more complicated. So, and this question arises obviously in text processing a lot and text generation a lot, because obviously you can describe any situation with a very lot of phrases, with a very infinite number of phrases. So, and there are actually very good research on how to work with this non-binarity. Okay, let's say so. With this non-binarity on question answering, because
yes,
for
exactly.
answering you can just say everything in a very different way. So obviously there is the same space of various non-matching answers which would match the question itself. So they designed special loss functions, and there are special procedures of how to change phrases from one to another. So I believe that would be somehow fruitful, and you can not just take ideas, but also have inspiration from how they solve it. Of course, they also have still a lot of problems with this, but they have some good guesses. So maybe it would be helpful for you to just check what they do.
Yes. Yes, it's actually, yeah, you mentioned the text example, which is like, yes, it's very well-known problem to have like non-binary matching. And it's also present in images in cases like face recognition, where like you want to match the same face or the same person, but with different pictures, like different faces. So that's like maybe a very similar problem in a way. This,
Yeah, it's very
very
common
interesting.
actually.
Yeah,
Yeah.
yeah,
And also I really like the second idea. So especially now, because generating methods are very cheap, so you can widely use them for pre-training all this synonymous sequences and all that similar images you can generate. So like this is good even if you don't put a lot of effort and just take generative models, and also if you put more effort and try to let's say guide how you generate things by, I mean, guide the prompts and
yes,
use it more wisely, it will also yield in efficiency for the master models. So yeah, I believe this is a really
yeah. Actually, yes. I tried to think about this, like, so like if we are talking about purely generative, I think that one of the most fundamental questions here is, can we find a way find a way to generate pairs instead of single modalities, maybe. So basically, I want the model to be trained to generate a pair of image and text, like regardless of what the pair represent. So yes, it can be like, for example, conditioned or something, but it will be very interesting. I agree.
mhm. So okay, actually my questions are finished. So if no one else wants to ask something, then I think that's yeah, we'd like to thank you for your talk.
Yeah, thank you. Thank you for it.
And happy holidays to everybody.
Happy holidays, happy New Year, everybody. Bye bye.